This is question 13 from paper 1, June 2018 AQA, A-level question, and it's a 10 marker, so I'll put that up here as a reminder. It's obviously quite significant right at the end of the paper, and it's asking to work out the maximum area of a pendant, which is basically a rectangle, we're told, inside a circle of radius 4 inches, so therefore the diagonal across is going to be 8 inches. Because we're told it's a rectangle, we cannot assume that obviously the two side lengths are the same. You might be tempted to just say the largest area possible is square, but we have to prove it. And it also says we need to fully justify this, which I'll get to in a minute. So we know our area, capital A, is simply the product of the two side lengths. Now, we also know that there's a relationship via Pythagoras, that a squared plus b squared equals c squared or 8 squared, 64. So we can make a substitution either or, so we can say a squared equals 64 minus b squared, or a is equal to the square root of this. Okay, so we can now represent our area A in terms of just a one variable. So obviously I'm going to substitute a as 64 minus b squared. I'm going to put b on the outside, we get root 64 minus b squared. So what we need to do is find out the maximum area. So in terms of calculus, we need to differentiate this function a with respect to b and set it to 0, so i.e. try to find its turning point, and then work out or solve for the value of b. Okay, so we're going to have to differentiate this rather horrible looking function. So this function is basically a product of two functions of b. So we're effectively saying that a is equal to u multiplied by v, where u, I'll put this over here, is equal to b, and v in this case is equal to 64 minus b squared. I'll put it as a power to the half. Okay, so when we're differentiating a product, so we're effectively saying dA by dB is what we're after, is basically equal to u dv dB add v du dB. Okay, or sometimes written uv dash plus uv dashed. So we need to differentiate each of these functions, u in terms of b and v in terms of b. Obviously this is very straightforward. Du by dB is equal to 1, but the one on the right, not so much. We're going to have to use the chain rule. So I'm going to introduce another variable. Predictably, I hope your knowledge of the alphabet is w, so v is w to the half. So I'm going to sort of move this down here to get a little bit of room. So using the chain rule, dv by dB is equal to dv dw times dw dB. Okay. Obviously, if you look at the chain rule, you cancel the dw's and you get the dv dB we want. So let's go ahead and try this, shall we? So dv dw, that's the easy bit. So dv by dw is equal to 1/2 w to the negative half, bring the power down by 1. dw by dB, and we know that w is equal to 64 minus b squared. So dw by dB is equal to, that's obviously disappeared, being a constant, negative 2b. So if we find the product of these up here, so we're effectively multiplying dv dw by dw dB, getting the dv by dB we want, which is going to be equal to negative 2b, well, that side multiplied by 1/2 w to the negative 1/2. 2 multiplied by 1/2 disappears, so we end up with 1 over w to the half. Okay, and we know from up here, w to the half is v, which is equal to negative 1 over 64 minus b squared, all to the half underneath. Okay, so we've got our components to go ahead and do our differentiation using the product rule. So that's step 2. So I've got rid of our workings on the right hand side and just simplified things. So we've got du dB and dv dB, which are our components to plug into our differentiation using the product rule to get our dA by dB, which is obviously what we're hoping to get. So dA by dB therefore is equal to U, make sure I get this right, so U, which is B, multiplied by dV dB, so it's going to be negative B over, I'm going to use the square root sign now, square root of 64 minus B squared, and then plus V, which is this thing, multiplied by du dV, which is 1, so it's just going to be square root of 64 minus B squared. Okay, so here we have the derivative of our function in terms of B for our area. Now we're going to set that to 0. Okay, so let's just get rid of that. Set it to 0 to have to rewrite the whole thing. Okay, so what I would do at this point to eliminate this fraction is just multiply everything through by 64 minus B squared. So I end up with negative B plus 64 minus B squared. So I've multiplied this, get rid of the fraction, multiplied by this, which will get rid of the square root sign, set that to 0. So we get 64 subtract 2b squared equals 0, or divide through by 2, and then we get b squared equals 32. Okay, so b is equal to root 32, which 16 multiplied by 2 is 32, so we get 4 root 2. So there's our value of b, which is one of the side lengths of our, I use the word rectangle for now. Now, if we sub this back into our relationship connecting connecting A and B, okay, so we know that, so let's go back up and remind ourselves, A squared is equal to 64 minus B squared, okay, so if I plug B squared into here, which is 32, so I know A squared is equal to 32 as well. Nice simple substitution. So A is also equal to root 32, which is also equal to 4 root 2. So from this, we can say that A and B are equal. So our rectangle is a special case and it's a square. So we can now just go ahead and put our two side lengths, 4 root 2 and 4 root 2. And therefore, let's get rid of this. We know that our area of our now square of the pendant is 4 root 2 times 4 root 2, which happens to be 32 square inches, which I'm not going to write down. Now, we might be celebrating this point and thinking we got 10 marks, but that's where you'd be wrong. Okay, there's a little twist in this. So the little twist I just mentioned is the phrase fully justify. Now that catches a lot of students out, and in fact it says so in the examiner's report that very few students got this mark. So what does it mean? It basically means we found what we think is the maximum area, but we don't know this. We could have actually found a local minimum because we simply set the derivative to 0, which doesn't distinguish. So let's just assume for the time being that we have a local maximum, okay, at, in this case, b was equal to 4 root 2, okay, and you'll notice that the gradient will be positive on the left-hand side, i.e. the smaller value of b, and negative on the right-hand side. Now, we could find the second derivative and see if it's positive or negative, but that would be horrible because of the nature of the function. So all we should really do is plug in, for example, 3 root 2 over here, and plug in, for example, 5 root 2 over here, and see if we get a negative value and a positive value. In actual fact, when you do that, you do get positive on the left-hand side, i.e. with a smaller value of b, and a negative value on the right-hand side, which is the larger value of b. And therefore we can say, therefore a maximum. So there's our full justification, and that would be worth the extra mark. Okay, so a little bit tricky on the end there. Okay, that was a pretty horrible question I dug out there. Thanks.